Hi, in this video, I'll be continuing our journey in probability. In the previous video, we have covered what's a continuous random variable, and so now we'll talk about different types of continuous random variables distributions that are very common. And so, there are many, but I've chosen this few to go through because they are quite a good source to understand continuous random variable. So one of the most common distribution is known as the normal distribution. You can hear it very often, such as when you have your exam grades, then the teacher says it follows a normal or bell-shaped curve. So the bell curve is really what people describe to be a normal distribution. And really that's because a normal distribution has the following property where we say x is normally distributed, and so we say x follows a normal which has the parameters of mu and sigma. So mu is the expected value, so it's the mean, and sigma squared is the variance. And then how we get this later, I won't show you, but I'll explain to you. But the density function is basically this complicated thing which we can kind of like black box it. And really when you have this density function, people have already shown a lot of properties about it, very nice properties that we can use. So one of it is bell-shaped, symmetric about the mean. So it's really what you want to describe as the bell shape, the bell curve basically. So this is it's called as the standard normal with the mean 0 and the standard deviation 1. And standard deviation 1, when you square it, is still 1. So that means variance is 1 here. And for the bottom one, it is really an arbitrary mean. And the sigma is something also arbitrary. And so this is the normal, that standard normal distribution. And the bottom one is just a normal distribution. And you can see how the bell-shaped curve and symmetry allows you to say that the probability x is, let's say this is minus x. So this is the probability x is less than or equals to minus x. If you to flip it over and this is x, then it is equals to 1 minus. You minus away this whole thing, you left with this. And so it's the probability 1 minus x less than or equals to normal x. So it's the positive x. So you can just see this equals to probability x is greater than x. So one is there is minus x, so you take so this is what I know as the left tail, the other one the right tail probability. So really this is quite useful when you want to find things or when you want to compute probabilities. And when it's normally distributed, then we can also have the following property that any linear function running through this x will also be normally distributed. So as long as your y equals to ax plus b, it is normally distributed. And this gives us the property that we are able to transform a standard normal to one with a general mu and sigma squared. And we can also convert it back. And so how we do it is, if we want to convert a standard normal to mu to sigma squared, we just need to multiply by sigma squared plus mu. And the reason why is because now you see that the expectation of x equals to the expectation of mu plus the expectation of sigma z. And sigma z is 0 because now you pull out the sigma, expectation of z, and expectation of z is 0. And so what you're left with expectation of mu, and expectation of mu is just mu. And so you see it has the expectation of mu. Expectation of x equals to mu. So you have one parameter. You can likewise show that the variance of x is sigma squared. And so with the expectation and variance, you are able to say x now follow normal with whatever expectation and whatever mu you want. And so really how we get this, why is the expectation and the variance that is really when you were to integrate this function, you realize that this value over here will be the expectation and the bottom value will be the variance. So really, but we really don't want to keep integrating this, so we just say that x follows a normal with the parameters of this expectation mu and variance sigma squared. And so if we want to convert it from a general normal to a standard one, it is known as standardization. And that's really more of what we want to do. So what we do is we take x minus away mu now, and you divide by sigma. And you realize this will work out to have the expectation of 0 and a variance of 1. The next distribution that we want to look at is the uniform distribution. And it is a very simple distribution. It is how we denote it is always uniform from A to B, where A and B is just some interval of a real line. And so what we want to capture is that the probability being proportional to the length of the interval. And so when we have a distance, say for inside A to B, so a sub-interval, say x to x2, x1 to x2, and it has the same length as the distance from x3 to x4, we want to capture the idea that they are the same probability when you integrate them over. And so in order to do so, for any length, for any equal length sub-interval, it has to be a constant basically. And so let's say now you have a sub-interval from alpha to beta. In order to keep the total probability to be 1, means the total area must be 1. Beta minus alpha whole thing times some constant must equals to 1. And this constant over here, this height, is just 1 over beta minus alpha. And so really it's very simple. Once you're given an interval, you'll know the height because it has to be 1 over that thing. The length of the interval. And so this is the PDF of x. And we can see from this example how we want to integrate it. To find the expectation, basically we integrate it from minus infinity to infinity and then restrict it to alpha and beta, because that's where all the values are defined only. And it's really x over beta minus alpha. And really it's so simple because now it's just x squared over 2 bracket beta minus alpha. And then you evaluate at beta minus away evaluation at alpha, and you result in the following. And you see that you result in alpha plus beta over 2, which is very intuitive, because if you have a constant function, the expected value will be the midpoint. So now you want to find the variance, you just need to calculate ex squared, and then you minus away ex whole thing squared. And really when you simplify, you just get the following. So I hope we see how we want to use the normal distribution and now the uniform distribution. But the best part about the uniform distribution is this thing known as the inverse transformation method. And really what you want to capture is that you have a uniform distribution and you know a CDF of something, or you stimulated from a computer the CDF of something. Then what it is that if you were to run this CDF, the inverse of this CDF, and evaluate it at this uniform, this random variable now will follow the CDF. And by following the CDF, we already know that it follows the PDF, and so it follows the distribution of the supposed generated CDF. And so we'll just prove it by showing that this F inverse U follows the CDF. And really, if you just let this be X, it follows naturally, because now F inverse U is less than or equals to X. You take the CDF on both sides, it won't change the sign because CDF is monotonic. And so u is less than or equals to fx. And really, this just means integrating from 0 to capital Fx 1 dt, because this uniform has a PDF of 1. And so you result in the following of fx only. And so since the probability of the random variable x, the CDF, is the same as fx, it says that the x follows a distribution whose CDF is fx, capital Fx. And really, that just means now, because x equals to this, it just means that if you run the inverse of a uniform of a function that you want by an random variable that follows a uniform, you get back the distribution. And actually, you can see that part 2 of the inverse transformation method, which is somewhat like converse, is that you have now a CDF. So you follow some function, and you let u equals to the CDF going through x, and this u now will follow a uniform from 0 to 1. And really, how to prove this is really, if you understand the following proof over here, is that now probability of u less than or equals to u equals to the probability of fx less than or equals to x. And really, this is just saying that the probability of x is less than or equals to f inverse x. And since x follows f, this is just f bracket f inverse x, so it's just x. So now the probability of u less than or equals to u equals to u, which means it's proportional to the length. And by being proportional to length, it just follows uniform, basically. So really, now you get a method of converting a uniform to the distribution you want, and from a distribution you can get a uniform random variable. So this gives you a method of generating random variables that follows a distribution that you want. And so it's very useful in stimulating random variables for a computer. So I've come to the end of this video. I'll explain more about different distributions in the next video, and then we'll move on from there. So thank you for listening, and I hope you have enjoyed it. Feel free to like, share, and subscribe, and I'll catch you out again. Thank you.